Okay, so we've sort of discussed how we get the shape that we see in VSEPR. Now let's take a look at exactly how these orbitals overlap to create a bond. So let's just go over this idea of orbitals. So remember that an orbital can be defined as a container that can hold a maximum of 2 electrons. We can also draw a representation of this orbital, both as electrons in a square box or as the actual shapes defined by the wave equations. Lastly, we can think about orbitals as being a mathematical equation that describes the probability of finding an electron around the nucleus. Now, when we're thinking about bonding, what's really happening is that these orbitals are overlapping. So if we take a look at hydrogen, it combines to form H2, a diatomic molecule. One electron from one hydrogen combines with another electron from another hydrogen. If we were to take a look at the orbital diagrams, we can actually draw the electrons in the boxes. Each has one electron in the 1s orbital. And again, these are atomic orbitals because they represent the electrons in the atoms. We can then draw the same thing, but this time drawing the electrons as being in molecular orbitals. So we combine the atomic orbitals to form a bonding orbital. And those electrons originally just attached to the atom are now in the bonding orbital. Now you'll notice that we form 2 bonding orbitals. One's lower energy, one's higher energy. They feel exactly the same way. The lower energy bonding orbital is where we have our electron density that is between the 2 nuclei. So if you take a look at the picture that I've just drawn, that is a sigma bonding orbital with the electron density between the 2 nuclei. Taking a look at the higher energy bonding orbital, this is known as an anti-bonding orbital, sigma star, and this is when our electron density is not between the nuclei, but in fact all the way on the other side, on the opposite side of between the nuclei. And this actually has mathematical origins. So specifically, a bonding orbital is made by summing the atomic orbitals. So remember that we can describe orbitals as mathematical equations for the probability of finding an electron. Specifically, bonding orbitals are made when we sum those equations. Anti-bonding orbitals are made when we subtract those equations. Anti-bonding orbitals are higher energy, and so the electrons will fill the bonding orbitals first. Now, the important thing to remember here is that a sigma bond is where we have the electron density between the 2 nuclei. So you need to be able to differentiate what is the difference between a sigma and pi bond, and again, this sigma bond is when we have the electron density between the 2 nuclei. Now let's take a look at another example, but this time instead of having our valence electrons in the s sublevel, let's take a look and see what happens when we have it in the p sublevel. So if we take a look, I can draw my p atomic orbitals, then I can draw my bonding orbitals in between them. I have 1 electron in each p, which will go to the lower bonding orbital. And again, I'm drawing the shapes here of the p, and what happens when the p's form a bonding orbital is that they don't actually form the electron density between the nucleus, they sort of bond sideways. So there's sort of a top and bottom lobe overlap, and this is known as a pi bond. And again, this pi bond is when we have electron density that is not between the nuclei. In fact, it is a sideways overlap of my p orbitals. And again, similarly, a pi bonding orbital is formed by adding the 2 equations for the p orbitals, and pi star is formed by subtracting. Now, the most important thing here to remember is this idea of what are the types of bonds formed for a single, double, and triple bond. So when you have a single bond, it's a sigma. When you have a double bond, it's a sigma and a pi. When you have a triple bond, it's 1 sigma and 2 pi. That is probably the most important bit to remember.